Hello, Assalamualaikum. Welcome back. In this video, I would like to explain to you on the continuity equation. So, when a fluid is in motion, it must move in such a way that mass is conserved. In fluid mechanics, the conservation of mass for a system is called continuity equation. When we say a mass, it means a volume of a fluid that coming to the system and leave the system. So first of all, I would like to disclaimer, material in this video are adapted from various sources, especially our reference textbook, Fluid Mechanics Fundamental and Application, and also from YouTube channel Strong Medicine, the Continuity Equation. So the objective of this video is to explain and to define properties of fluid flow and understand how conservation of mass principle in control volume can help ones to determine fluid properties such as velocity, cross-sectional area, mass and volume flow rates. Let's have a brief introduction. How can you tell the volume flow rate of water in a pipe hose? For example, if you do have a pipe hose that connected to a tap, and then you want to know what is the volume flow rate or what is the flow rate of the water that coming out from the hose. Some of you likely will answer with something very simple and feasible. You let the water flow out from the hose and then let the water pour into 1 liter of bottle, and you count the time. You use the stopwatch to see how long it takes to fill up 1 liter of bottle. That's actually general definition of fluid flow. Flow is the volume of fluid that move past a certain point per unit time, because you can specifically tell that the flow rate of the water in the hose is actually equal to how much volume of fluid that coming out in how many seconds. Then you can have Q equal to volume over time. And you also know, we have learned this, flow rate is also equal to area times velocity. Let me show you how can we relate area velocity and volume over time. So let's see a pipe conduct here. You do have water coming from the left and then exit at the right, and then I put streamlines here. Let's take a section here, not far from the inlet. And then I call this as section 1. And then in this section 1, definitely we do have length 1, and then to have area 1. And then as you mentioned before, that flow rate is equal to volume over time. So I just write it down here again. Q equal to volume. How can we prove this is also equal to area times velocity? Okay, let's see step by step. So as we know, volume is equal to area times length. So in this section, equal to area 1 times length 1. If you put back to this equation, you will see Q equal to 1 times length 1, which is length 1 over time. And then we also know that whenever something moves from point A to point B, and then they do have length, and then you record the time, it will become what? L over T. It become velocity. So again, you go back here and you put velocity, and then it become area times velocity. Okay, so in this case is area 1 times velocity 1. The same thing I can do at the section 2, and then this one, and I can quickly tell that Q2 is equal to A2 times L2. Whenever the flow move from point here to here, it's always become Q1 equal to Q2, and then definitely it's become A1 V1 A2 V2. Physics always correct by saying that Q in section 1 equal to Q in section 2. However, there are some cases that Q1 is not equal to Q2 with something that
maybe fluid will back up somewhere and become compressed, and it will violate this theory.
So take home message here, whenever A1 V1, it must equal to A2 V2. This is an example of whenever you do have hose that attached to the tap, and then you want to know what is the velocity from the hose, V out, right? What we have to know? We have to know the cross-sectional area at this part, so A out. And then what is V in for the hose? Definitely it has to come from here. Alright, so this one is V in, A in. So according to the theory, Q in equal to Q out. So V in, area in, equal to V out, area out. And then let's say you want to know V out, so simply move to the area out to the other side, and then divided by A out, and then you can have a velocity out meter over second. So the overall principle of conservation of mass, as I mentioned before, total mass entering the control volume during interval time, total mass leaving control volume over time equal to the net change of mass. So we can simply write like this: mass flow rate coming, mass flow rate out equal to total change of the control volume over time. If you look at this is a good example of flow rate that coming in and coming out, and then there is change of mass in the control volume. Look at this bathtub. The water coming that fill in the bathtub from this tap, flowing mass in 50 kilogram. It's not over time, it's just mass in 50 kilogram. And then flowing out from that 30 kilogram. Definitely 50 is not equal to 30, right? 50 kilogram is not equal to 30. So where the 20 kilogram go? 20 kilogram of the water stay in this bathtub. So basically if you write it down, M in minus M out equal to M control volume, or you can write in the flow rate M dot in, mass flow rate coming, mass flow rate out equal to rate of change mCV over dt. I think some equations that related. I think I have to say the slide not very good, so just bear in mind there is volume flow rate. You will see this many times when you do the exercise, even in the test. We do have mass flow rate, so volume flow rate usually it represents by, let's say, like this, volume flow rate. So this symbols is always used in fluid mechanics, so don't get confused. Sometimes they use full term volume flow rate, sometimes they use this one. Basically volume flow rate is equal to what? Volume flow rate is equal to Q, and then Q definitely equal to what we have learned just now, area times velocity, or area times V. How about the mass flow rate? M dot equal to what? Rho, the density, times area times velocity, or we can simply put rho times volume flow rate. Remember this one. So we can replace this one by having this volume flow rate. However, there are two cases that we can always fully check our system. First one is you do have steady mass flow, which means, like, remember the conduit, the conduit, water coming here and out is steady flow. Definitely mass in this control volume doesn't change. Steady flow coming out in and coming out. So M in here must equal to M out. How do we know it is steady flow? Usually we have to check and give assumption. For example, like this system, although there are 2 inlets, P, A, and then 3 outlets. So from this system, they have steady mass flow rate. Total of mass coming in equal to total mass of out. So we can write MA plus ME minus MB minus MC minus MD equal to 0, because it's no mass change in the control volume. So, right, so when we write it down, it's actually not MA, it's actually what? Flow rate. Because of what? Rho times A times velocity. V here is velocity. So in your notes in column, so carefully double check and put the dot at the top of M, so that it will become mass flow rate. Remember, M is rho times A times volume. Sorry. Yep. Remember, M dot always equal to rho times area times velocity. Okay. So that's why they said here total inlet equal to total outlet. I have two exercises that we will do together after this. Another incompressible. So you do have incompressible flow, water that flowing in the tube or hose, and then it's not only steady but it says incompressible. Whenever it says incompressible, what you can do, you can take out the rho, because you know M dot is equal to rho times A times velocity. Whenever you do have M dot in equal to M dot out, and then the density is constant, you can still write M of the fluid times area at point 1, for example, and velocity at point 1, or in A in V in equal to rho of the water times area out velocity out. And then you simply can cross out the rho because the density doesn't change. That's why
area N in the inlet times V at the inlet is equal to A at the outlet and V at the outlet.
Let's have this example. Want us to carefully check what is the fluid properties at point A, point B, point C, and point D. What will be the discharge velocity at point B and C? Okay. So I put it smaller here so that we can analyze. So firstly, we have to give assumption for this equation, for this question. So, right, every problem we have to put assumption first. So I put firstly is it is steady flow. I say that because in the question it didn't ask or it didn't tell about anything that will change within the control volume. So secondly, it has control volume. So control volume, you can write control volume here. So we measure everything inside the control volume. So, and then third one, I can tell this is incompressible flow. What do I know? Again, it didn't say in the question. Usually if it's compressible, it will mention in the question. For this one, it didn't tell, that means it's incompressible flow. Second reason is you can simply tell from the velocity and from the diameter. So remember, to become compressible, you have to check with the Mach number. I explained to you in the video part 1.
The flow of the fluid has to be divided by speed of sound, and then the Mach number must be greater than 1. So this one is very small, not comparable with the speed of sound.
So let's do the solution. So as I mentioned, it is steady flow, incompressible, and it's within the control volume. What we can say, mass flow rate coming out minus mass flow rate coming out, and it is steady, remember, so it's become 0. So always mass flow rate coming in equal to mass flow rate coming out. So from this question we can tell that m dot at A is actually equal to m dot at B. M dot at B is actually equal to what? Equal to m dot at C times m dot at D. So given to us velocity at A, velocity at T, on velocity at B we don't know, velocity at C also we don't know. Okay, let's do this together. So as I mentioned, m dot A equal to m dot B. So basically it's steady flow. So okay, let's write in full. So rho area A velocity A equal to rho area B velocity B, and then because it's incompressible flow, the density is constant, you take out the rho, so it becomes AA VA equal to AB VB. And then the question asks us about velocity at B.
Simply mathematics, you put the VB as subjects and then you move the AB. AA VA divided by B divided by AB.
So area of A is diameter in, they give us diameter A 450 mm. So make sure it's in meter. So you change to meter, it becomes 0.45 meter. Okay, and then area for cylinder, this one is pipe, so you consider as cylinder. Area pipe, it's always pi d of 2 over 4. So you write it down for area A equal to 0.45 power of 2 over 4 times VA, given VA 1.8 meter per second, divide by AB. Do we know AB? Yes, we know AB as well. Pi 0.300 mm divided by 2 over 4. Then you can tell VB equal to meter per second. Simple, right? So straightforward question. You just have to make sure that you put correct value for diameter here, and then correct expression of area for the pipe, and must make sure you change from mm to meter. So velocity at C, we use this one. So this one. So MB is equal to, we don't need to put the rho again because we know that rho is constant because it's compressible flow. So you write AB VB equal to AC VC plus AD VD, and then you know AB VB because from here you know the AVB. So simply mathematics, VC is equal to m dot B minus m dot D divided by area of C. Then you can know VC equal to meter per second. That's it. Okay, let's see this example. The second example. This one is trickier than the previous example. In this question, they give us a system that have flow coming in and coming out, and then basically this system here has two mass coming in. Let's say m1, m.1, m.3, both are coming in, and then m dot out at 2. And then they have base area, and then they have height of the water, of the mass water in the tank. And then remember this one, volume flow rate equal to Q. And from this diagram or this figure, we can simply say that conservation of mass that have the rate of change of mass in the control volume. Okay, so we do have m1 in, m.3 in, and then m2 out. So we, as usual, give assumption based on the diagram. Assumption doesn't mean you can give any assumption, but you have to look at the figure, look at the question text, and then look at the system in the figure, then you give assumption. It has to be accurate as well. So assumption 1, incompressible flow. Correct. Let's just get the simple one first, which means what? The density is constant, rho constant. Second, this system has rate of change of mass in the control volume. Meaning what? The mass inside the system is changing. 3, it is control volume or open system. Okay, just to make sure that you can follow that 2 inlets and 1 outlets, and then this is the system, the boundary. Okay, so solution. Let's write the full equation or expression of the mass balance. So we know in this case this system has rate of change, so we write in full first, m dot coming in and total mass flow rate coming out equal to what? Rate of change mass in the control volume over time. I hope you follow. When I said something, it's really implied to what I wrote. Okay. So for the total mass coming in, we do have m.1 plus m.3, yeah, 2 flow coming in, minus m.2 equal to in the control volume. So how can we write this? This is very interesting. So we know mass in the control volume is also equal to, remember this, I hope you still remember, mass equal to what? Equal to area times length or height. In this case, with h equal to length, because h actually changing. So how can we write this? We write delta h. Okay, delta h, because delta h is changing, times area over time. You got it? I hope you got it. Okay, because what? Delta h over dt, h is changing over time. For example, if you do have high mass flow rate that coming to the system and then low mass flow rate that exit the system, definitely h will increase, which means mass in the system will be increased, right? So that's why you put delta h. So having this equation, we try to solve the problem. So question 1, they ask us if the h is constant. What you mean by h is constant? Meaning h equal to 0. Does it change? Okay. Sorry. When you say if the h is constant, meaning what? delta H is 0, which means at time, let's say time 1 second, H is 10 meter, the height is 10 meter. At time of 5 seconds, H is still 10 meter. So delta time, delta H, from 1 second to 5 seconds, delta H 10 meter minus 10 meter, so it will become 0 meter. That's what it meant by constant. So when you write the equation, it will become like this: m dot 1 plus m dot 3 minus m dot 2, right? M out, m dot out. Delta H A T, you replace delta H by 0, so it will become 0. So you can simply write m dot 1 A1 V1, velocity 1, area 1 plus m dot 3. M dot 3 they already give the flow rate, Q3. So Q3 0.012 meter cube per second minus m dot 2. M dot 2 we don't know, we only know area 2 and V2. So they want to know V2, you can simply use the same solution like in the previous example. So write down the area of and then the velocity at point 1. So velocity at point 1 given, right? Velocity at 0.15 meter per second. So A1 V1 plus 0.012 divided by A2.
So write down A1 is equal to 0.04 meter per second, meter, the diameter, times pi over 4, the area at 1, at location 1, times 5 meter per second, velocity at point 1, plus 0.012, and then divided by A2. A2 given to us, the diameter is 60 mm, so make sure it's in meter, so you write it becoming meter, 0.06, yeah, divided at power of 2, times pi over 4, then you can have V2 equal to how many meter per second.
You calculate by yourself. How about question B? Question B: if H increase at 4 mm per second, so delta H, what it means by increase by 4 millimeter per second, delta H equal to 4 mm per second. It is quite straightforward because you can just replace delta H to this equation, right? However, the quite tricky part here is millimeter per second. You have to change it first to meter per second. So mm convert to meter per second, it will become 0.004 meter per second. A1 V1 plus 0.012 minus A2 V2 equal to what? 0.04 delta H times what? Area of base area given here, 1 meter per second. You put it back to here, area base, okay, 1 meter per second. So basically exactly the same thing you have to do. Get it V2 from here, meter per second. Question C: if h decrease at 6 meter per second, if h decrease at 6 mm per second, so delta h equal to minus 6 mm per second, so it become convert to meter, minus 0.006 meter per second. So write it back in the equation. Sorry, plus 0.0212 minus A2 V2 equal to delta H here is minus, so minus 6 meter per second times A 1 meter cube. A is what? A is area base. Then you can get the V2 here as well. How about D? If H is constant, which means 0, right? And then section 3 is closed. Section 3 is closed. M.3 closed means what? Closed means 0 meter cube per second. So simple, right? You don't need 0.012 in the equation anymore. So A1 V1 minus or plus 0, because M.3 0, minus A2 V2 equal to what? Equal to 0 again, because delta H is constant. Then you can simply get V2 equal to A1 V1 divided by A2. Yeah, then meter per second. Alright, I hope you follow the equation. Sorry for my not very good handwriting here, but I just try to explain step by step how can you analyze the system. First, give assumption, and then in the solution try to give accurate expression. Whenever you do have incompressible flow, you don't need to involve delta anymore because the density always constant. And then if you do have mass in the control volume, definitely you have to involve the rate of change of the mass in the control volume over time, and then you do the calculation. Make sure mathematics, make sure you do the exercise for the dimension conversion from mm to meter, and make sure that you do the correct calculation. I think that's all for continuity equation. I think that's all for now. Thank you very much. See you in video part 4.